Let's start this section by taking a quick look at solvent effects in SN1 and E1. Whether you're dissolving your substrate, which could be an alkyl halide or a tosylate, so those are the two types of compounds that would undergo any of these substitution and elimination reactions. Whether you're dissolving it in a nonpolar solvent or a polar solvent, the difference there is not going to be that great in terms of the energy of what's going on. Where you see the greatest differences, though, is in the transition state. So if each of these are transition state structures that show the ionization in the process of taking place, so the bromine or the chlorine or whatever it is departing from the molecule to form the carbocation, notice that you have charge building up in that situation. A polar solvent is going to be able to stabilize that developing charge to a much greater extent than a nonpolar solvent. So a transition state for carbocation formation occurring in a polar solvent is going to be lower energy than the transition state for a carbocation formation that's occurring in a nonpolar solvent. All of which is to say that carbocation formation will proceed more readily and more quickly in a polar solvent versus a nonpolar one. In terms of polar solvents, though, the important distinction, as we've seen before, is the polar solvent protic or aprotic? And as it turns out, polar protic solvents do a much better job at stabilizing transition states leading to carbocations, as well as the carbocations themselves. What this means is that SN1 and E1 reactions are going to go fastest in polar protic solvents. So polar protic solvents better stabilize the transition states leading to carbocations. So remember, if you lower the energy of the transition state, so a stabilized transition state, we'll abbreviate transition state with that little symbol. Transition state stabilized means it has a lower energy, means a smaller activation energy, which corresponds to a larger rate constant and thus a faster rate. The take-home from all of this is that SN1 and E1 reactions run fastest in polar protic solvents. So that's why the examples that we've seen so far, for the most part, have involved polar protic solvents. You'll recall that a little while ago we talked about the stereochemical outcome of an SN2 reaction. Remember, in an SN2 reaction, the nucleophile attacks in what's called a backside attack from opposite the bond to the leaving group. And that if the nucleophile attacks an asymmetric carbon, the result will be inversion of configuration. SN1, on the other hand, now we want to look into the stereochemical outcome of SN1. SN1 can give mixtures of what we call retention and inversion of configuration, and that depends on various things. First of all, retention just means to be retained. So that means the configuration stays the same from starting material to product. So let's take a look at what's going on here. So let's say that we have this guy. We'll say that's our substrate that we want to have undergo an SN1 reaction. And so we have A and B and C and bromine. So let's also say that none of those things is the same. So A and B and C and bromine are all different, which means that the carbon that they're all attached to is an asymmetric carbon. So this guy right here is an asymmetric carbon. So the compound ionizes, starts out as a tetrahedral arrangement of the groups around that asymmetric carbon. The compound ionizes, the bromine takes off, and now what we have is a trigonal planar arrangement of the groups because the carbon has rehybridized to sp2. So this is a flat structure, the structure on the far right. So all the bonds from the carbon with the positive charge to A, B, and C are all on the same plane. Now if we take that structure and we tip it on its side so that it's perpendicular to the page, then what we get is a picture that looks like the one over on the left side of the screen. The p orbital associated with the carbon with the positive charge is empty, and that's the orbital that the nucleophile can attack. But because this thing is flat, so we can draw in some other. Because this thing is flat, it has two faces, just like an alkene. And so the nucleophile can attack from the top face, in this case, or the bottom face, or we could call them the front face and the back face if we drew the structure a little bit differently. But regardless, there's two faces and two possibilities for the nucleophile to approach. The outcome is going to be different depending on which face gets attacked. All of this is going to depend on how far away the leaving group has gotten before the nucleophile attacks. So in the next picture, we have a picture of the transition state. Okay, the transition state, again, denoted by this symbol here. So this is the compound in the transition state as the bromine is leaving. So the dashed bond, that dashed line, means that the bond is breaking or forming. In this case, it's breaking. The bromine is developing more negative charge. The carbon that it's leaving is developing partial positive charge. The structure is beginning to flatten out as this carbon rehybridizes. So if the leaving group doesn't get too far away, it's going to be easier for the nucleophile to come in from the other side, the other face, opposite where the leaving group is still kind of hanging out. That would be an inversion of configuration. But there are also cases where the leaving group is able to diffuse away through the solution and the nucleophile can attack from the same side of the cation where the leaving group just left from. In that case, the configuration is going to remain unchanged in the product from what it was in the starting material, and we would get retention of configuration. So both things can happen. It's not like SN2 where only inversion can happen. So in SN1, we always get a mixture of products. That is both inversion and retention of configuration. But typically, it's the inversion product that we're going to get a bit more of. Okay, so you always get a mixture, typically with more of the inversion product. All right, now let's draw some mechanisms and take a look at what's going on in some examples. Now that we know something about the stereochemistry. Okay, so first of all, what do we have going on? We have a tertiary substrate with a decent leaving group. It's in water, which we know to be a weak acid, a weak base, a weak nucleophile, and a polar protic solvent. So you might be wondering why every time we look at water or an alcohol, we include in our list of the things that we know about it the fact that it's a weak acid and a weak base, even though it's not acting as an acid or a base in this context. The only reason for doing that is to remind you of that so that you can continue to remember the roles of water in these various things. Okay, so we have that information. So now let's make an assessment. Let's rule some things out. So remember, we have to pick from one of 4 pathways, or at the most 2. So what we can rule out right away is SN2. And the reason that we can rule it out is because we have a tertiary substrate that's too hindered to allow a facile SN2 reaction to occur. We also have a weak nucleophile in water, which also discourages an SN2 pathway. Another pathway we can rule out would be E2, because there's no strong base. So again, that's why we want to be able to identify water in terms of its acid and base strength, so we can do things like rule it out as a strong base, so that we know that there's unlikely to be much E2 going on. So that leaves us with SN1 and E1 as the remaining pathways. And so we're going to draw the mechanism for SN1. So to start out with, the compound ionizes. Now, the carbon that the chlorine started out on was sp3. When the compound ionizes, it becomes sp2, and as such, it develops a trigonal planar geometry, which means that all 3 of the bonds to that carbon must be drawn in the same plane. Now the water can attack. And we'll draw the stereochemistry in a minute, but it can attack from the front face or the back face. Notice for that carbocation, there was no potential for rearrangement to a more stable carbocation, so we left it alone. So now we get to this intermediate, and by now we know what to do with it. We will deprotonate it. And that gives us the product. Okay, so now let's draw the products with stereochemistry. So if the water attacks the front face, as it does so, the carbon it's attacking rehybridizes again and becomes sp3 again. So if the water came in from the front, then you'll end up with OH pointing forward, which pushes back the methyl group. On the other hand, if the water attacks from the back face, now it's the OH group that's going back and the methyl group that's gotten pushed forward. The product on the left is the product of inversion. It has the opposite configuration as the starting material. The product on the right has the same configuration as the starting material. It's showing retention of configuration. Let's do another one of these. So once again, a tertiary substrate, so lots of steric hindrance there, a good leading group, with a polar protic solvent that's a weak acid, a weak base, and a weak nucleophile. The fact that it's a weak nucleophile suggests less or no SN2. The fact that it's a tertiary substrate also suggests no SN2. And so we have a substrate dissolved in a polar protic solvent by itself. So like we've seen in all these other examples, that's a solvolysis reaction. So the reaction starts with the compound ionizing. And notice when it does so, the bonds around that carbon that has the positive charge flatten out. Now the nucleophile can attack. And just like the previous example, it can attack from the top face or the bottom face of the planar carbocation. We won't show stereochemistry yet. We'll finish the mechanism and then we'll draw the stereochemical outcomes. As you might imagine at this step, another molecule of methanol acts as a Bronsted base and removes this proton. And that completes the reaction. So you're going to have two possible outcomes. And in both of them, the methyl group at the top of the structure stays in the same position. It hasn't been involved in the reaction. Nothing happened at the carbon it was attached to, so it stays the same. So you'll have the product of retention of configuration, which will look like this. And the product of inversion. So we've taken some time looking into the details of SN1, goes through a carbocation intermediate, and typically many of the SN1 examples that you're going to see are going to be like the ones that I've showed you. They'll be solvolysis types of reactions, where the solvent is participating as the nucleophile. And so one way to help recognize those is that you'll have a hindered substrate and a polar protic solvent, and nothing else dissolved in there. So you won't have any other reagents or other nucleophiles that could also react.